Good afternoon, everyone. Today, I'm excited to talk to you about a fascinating and revolutionary tool in the field of nanotechnology, the Scanning Tunneling Microscope, or STM. This incredible instrument has transformed our ability to observe and manipulate matter at the atomic level, providing insights that were once thought impossible. The scanning tunneling microscope was invented in 1981 by Gerd Binning and Heinrich Rohrer, that you can see in the picture. Their work earned them the Nobel Prize in Physics in 1986. The STM is a powerful type of microscope that uses quantum mechanical effects to image surfaces at the atomic scale. Before jumping into how does the STM work, let's quickly introduce the principle underlying this technique, the quantum tunneling effect. What is tunneling? In classical physics, if a particle doesn't have enough energy to overcome a barrier, it simply cannot pass through. However, in quantum mechanics, particles exhibit behavior that defies classical intuition. One such behavior is quantum tunneling. Quantum tunneling is the phenomenon where a particle passes through a potential barrier that it classically shouldn't be able to cross because it doesn't have enough energy. This occurs due to the wave-like properties of particles at the quantum level, as described by the principle of quantum mechanics. To understand quantum tunneling, let's break it down to a few concepts. Wave-particle duality is the first one. In quantum mechanics, particles such as electrons exhibit both particle-like and wave-like properties. This duality is described by their wave function, a mathematical function that provides information about the probability of finding a particle in a particular location. Second, we have the potential barrier. Imagine a potential barrier which can be thought as a hill that a particle needs to get over. In classical mechanics, if a particle's energy is less than the height of the hill, it cannot cross over. However, in quantum mechanics, the particle's wave function does not stop at the barrier. Instead, it decays exponentially inside the barrier, but still has a finite probability of appearing on the other side. Finally, we have the key concept of tunneling probability. This is the probability that a particle will tunnel through a barrier, and it depends on the width and height of the barrier, as well as the particle's energy. Mathematically, the probability decreases exponentially with the barrier's thickness and height, and this can be expressed by the formula in the slide, where we have that the probability is proportional exponentially to k, which is a constant that depends on the mass and energy of the particle, and d, the width of the barrier. The basic principle behind STM is relatively straightforward, yet very powerful. It involves the use of a sharp conducing tip that is brought very close to the surface that is being studied. Here's how it works. First of all, we have quantum tunneling, as we talked about. When the tip is brought close enough to the surface, a voltage is applied between the tip and the surface. Due to quantum tunneling, electrons can tunnel through the vacuum between the tip and the surface, creating a measurable tunneling current. We have then a feedback mechanism. This tunneling current is extremely sensitive to the distance between the tip and the surface. And by maintaining a constant current, the STM can adjust the tip's height with extreme precision. This adjustment provides a topographic map of the surface at the atomic level. Finally, we have atomic resolution. The resulting data is processed to induce an image that reveals the position of individual atoms on that surface. So summarizing the workflow, we first have the initialization, where the tip is positioned close to the sample and a voltage is applied to initiate the tunneling current. Then we have the scanning, where the tip moves across the surface and the tunneling current is monitored. We have then feedback adjustment, where the system adjusts the tip's height to maintain a constant current following the surface contours. We collect then the data. And finally, we construct the image that is going to be a high resolution image of an atomic structure. How can you be so sensitive though? There are a few reasons that allow STM imaging to be this good, to have a magnification of 100 million and a resolution of 0.1 nanometers. First of all, the atomic scale sharpness of the tip. The tip of the STM is made from conductive materials, like tungsten or platinum iridium, and is often sharpened to a single atom at the summit. The atomic sharpness of the tip ensures that the tunneling current originates from a very small area, increasing the spatial resolution. A sharper tip can interact with individual atoms on the surface, providing detailed information about atomic positions. Moreover, the STM uses piezoelectric materials from its scanner, which can move the tip with atomic precision. Piezoelectric materials expand or contract in response to an applied voltage, allowing the tip to be positioned with sub-Armstrong accuracy. This precise control is crucial for maintaining the correct distance between the tip and the sample, and for scanning the surface accurately. Finally, the STM employs also a feedback loop to maintain a constant tunneling current by adjusting the tip's height. Given this high precision, it is possible to obtain high-resolution images at the surface, as in the following pictures, where the structure of the molecules is quite clear. STM offers several unique advantages. First of all, high resolution. Then also versatility, because the STM can be used in various environments, including ultra-high vacuum, air, or even liquid. Then also manipulation capability, because STM can also be used to manipulate atoms and molecules, enabling the construction of different types of nanostructures. Despite its incredible capabilities, though, STM doesn't have just advantages, but also some limitation. The most important one to keep in mind is the surface requirement, because it requires conducting or semiconducted surfaces to function, which limits the type of materials that can be studied with this technique. Technical complexity is also a limitation. In fact, STM requires sophisticated equipment and skilled operators, making it less accessible. Sensitivity to environment is also to keep in mind, because STM is highly sensitive to vibration and external noise, necessitating a control environment for accurate measurements. In conclusion, the scanning tunneling microscope has revolutionized our understanding of the atomic world. Its ability to image and manipulate individual atoms had opened up new frontiers in science and technology. And as we continue to explore the nanoscale, STM will remain an essential tool, driving innovation and discovery. Thank you for your attention. I hope this talk has provided you with a deeper appreciation of the incredible capabilities and impact of scanning tunneling microscopy.